Hello, students. Previously, you have learned how to graph the sinusoidal functions, which are the sine and cosine functions. In this video today, we're going to look at the graphs of other trig functions. Primarily, we will be looking at the graph of a tangent function. Just like I use the table values of some of the common angles from the unit circle to look at the shape of the graph for sine and cosine functions, I have a similar table for the tangent values of the common angles in quadrant 1 and 2. As you can see here, we know that tangent of 0 is 0. Tangent of pi over 6 is root 3 over 3. I'm going to get a decimal approximation for root 3 over 3, and that is about 0.577. Tangent of pi over 4 is 1. Tangent of pi over 3 is root 3, which is about 1.73. Tangent of pi over 2 is undefined. In second quadrant, tangent values are negative. 2 pi over 3 is negative root 3, so negative 1.73. 3 pi over 4 is negative 1. 5 pi over 6 is negative root 3 over 3, which is about negative 0.577. And tangent of pi is 0. And these values will repeat in the third and fourth quadrant. Once we plot these points here, as you can see, tangent of 0 is 0 right here. Tangent of pi over 6 is about negative, is about 0.577. Tangent of pi over 4 is 1. Tangent of pi over 3 is 1.73. And these values, as you can see, are increasing, and they start to increase without bound as your angle approaches to pi over 2, which is why you have a vertical asymptote here. Vertical asymptote, as you know, is a line to which your graph as your graph approaches to that value where this vertical asymptote is, it either increases or decreases without bound. So tangent values undefined at pi over 2. It is also, if I continue this table, it is also undefined at 3 pi over 2, which is same as negative pi over 2. So you can see here, because these tangent values are increasing on the left of this, 2 pi over 3 just continued on the right, but I did not go on the left. Like if I go negative pi over 6, these values would start to decrease, and then they will be decreasing without bound as the graph will approach negative pi over 2 on this side. I'm not able to write past this point, but these values are going to decrease on this side and then approach to negative infinity as your angle approaches to negative pi over 2. So looking at this graph of a tangent function, we know that there will be a vertical asymptote, not just here at pi over 2 and negative pi over 2. If I extend it, there will be another asymptote at 3 pi over 2, correct? And on this side also, there will be another vertical asymptote here at negative 3 pi over 2. So when we write an equation we were not able to list all of these vertical asymptotes, but when we write an equation for vertical asymptotes, we just say x equals to pi over 2 plus k times pi, where k is an integer. So any integer multiple of pi, if you keep adding, or if you just keep adding pi, like for 3 pi over 2, if I add another pi, then I'll have another vertical asymptote. And same thing, if I keep adding the negative values of pi, there will be asymptote on the left-hand side. So k is an integer. Integers are both positive and negative, so you will have all of the asymptotes, vertical asymptotes in this tangent function. When we will plot the graph, when we'll make the graph, we'll only plot 5 critical points, just like we were plotting 5 critical points for sine and cosine, just to get one cycle, and then the pattern just continues. We will use the 5 critical points in tangent functions as well. 2 of those critical points are where your asymptotes are going to be, and 3 critical points in the middle. The very middle one will always be at the midline. In this case, the midline is your x-axis, There's no shift in the graph, no vertical, horizontal shift. So tangent of 0 is 0 right here. And then we'll plot this point halfway between 0 and pi over 2, which is pi over 4. The tangent value is 1. If I have a different value of a, for example, if I had tangent of 2 times tangent of x, then tangent of pi over 4 is 1, but 1 times 2 will give me 2. Then I would have plotted that point here. So just know that A is what will give you this point, okay, at halfway between 0 and the asymptote. And if it's not even 0, wherever your midpoint is, or wherever your midline is, your graph is crossing through the midline in that cycle, halfway to the right, when it's halfway through to the right vertical asymptote is going to be at A, and the halfway to the left vertical asymptote is going to be at negative A. If it's reflected, then it will be obviously multiplying that y value by negative. That will make your graph just reflect like that. Okay, so let's look at some characteristics of our tangent graphs. So we can see that they're periodic in nature. All trig functions are periodic in nature. This cycle just keeps repeating, and the period of tangents is pi. Just remember that. The domain is not all real numbers. It's all real numbers except for where you have the vertical asymptote. So they're not continuous, unlike sine and cosine. The range is all real numbers, negative to positive infinity. What values we exclude are the values where we have the vertical asymptotes. And if you notice that the tangent functions are symmetric about the origin, which means that you have a lot of cycles. They are odd in nature. So tangent functions are odd functions, just like sine functions are odd functions. Cosines are even. Let's look at the general equation, or the standard equation, which will help us in graphing the transformed functions. As you notice here, you have the same parameters, A, B, C, and D. Their roles are also same as in any other trig function. In fact, any function for that matter, the transformations rules are same. A in this case we will not call that an amplitude, but it will be the determining factor of the vertical stretch or shrink, and that is the point that we will plot. Two of the points we will plot, one at A and one at negative A. B will determine the period, and in this case you will be dividing the pi, not the 2 pi by the absolute value of B in order to determine the period of the cycle of the function. Same thing here, the phase shift will be determined by using negative C over the absolute value of B. And if your equation is given in the form where B is factored out, then you will not have to divide by B. D is the vertical shift up and down. This will also be the midline of your graph. That's where halfway between the asymptotes is going to cross at the midline. So short and sweet introduction about the tangent functions. In the next video, I will be graphing some of these transformed tangent functions. So stay tuned.